Good morning. Hopefully you guys are doing all right. Let me do the usual things. Here are links. Here are links to the attendance and the tutoring and to the end of quarter eval for the class. If you guys have a chance, please go fill it out. It's only 5 questions and we just pick a choice. So all of those should be easy to do. Let's see. For the end of the quarter evaluation for COSTA, COSTATS 13. I'm like, COSTA, what's COSTA? COSTATS 13. What would you like to give feedback about today? Should I choose workshop, class, special experiment, individual experiment? I guess class is, yeah, it's a co-class. So yes. Oh, I'm frozen. Am I still? Am I frozen still? Is it just Kimberly? So everybody, let me ask. Okay, let me. Oh, the evaluation is more than 5 questions? Huh. The one I see is 5 questions. It's just there's a lot of options for each question. Okay, it looks like so. There's an arrow. Oh, there's an arrow. Ah, I'm super smart. Okay, there's like 9. Okay, there's. Oh, I have to answer the questions to get to the next one. So there's more than 5 questions. So from the responses in the chat, it looks like Kimberly might be the only one I'm frozen for. So here's, yeah, so I was just gonna say, if I'm frozen for you, I would try exiting and rejoining. All right, let me see. I feel like there was something else I wanted to mention. No. All right, hopefully Kimberly. Okay, Kimberly. Frozen still? Oh, good. Awesome. All right, cool. So once again, here is the attendance link, which everyone please go fill out. The link to the tutoring as usual, and then the end of quarter eval, which apparently has more than 5 questions on it. Still, it shouldn't take too long, so please do go do it when you have a chance. There was something else on my brain. Oh yeah, the quizzes. I posted the solution to the quiz. I haven't graded it yet. My plan is to grade it today. I meant to grade it yesterday, but I got caught up doing other things. So I will definitely get that graded. And yes, today is the Nimjari day as usual. And I guess I should ask, do you guys have any questions, specific questions or general things? I have an idea of what I want to talk about, but if there are things you want to see, you are always welcome to suggest things. And I'll wait for a minute. Sure. So let me ask you, Kimberly, when you're talking about large versus small sample tests, are we talking about hypothesis testing, or are we talking about confidence intervals, or I mean, which are kind of the same, really? But like, what kind of test do you specifically mean? Okay, cool. That's what I thought you meant. All right. So actually, I think I have some stuff that I think is worthwhile. So let's go ahead and I'm gonna. So I'll post this handout on Canvas after class. In fact, let me, so I'll post this on Canvas now on after class, just so you guys can see it. But let's actually walk through this handout here because I think it is worthwhile. Let me just minimize other things so there's not so much going on my screen here. Share a million things on my screen. Okay, cool. So let's look at this. And this might actually require, well, yeah. So let me share my screen. There we go. So let's look at this handout here. Let me move this garbage over here. Cool. More chat. Awesome. Great. Okay. So, and then the reason I minimize this here is just so we don't have to look at all of it all at once. So, hypothesis testing for a mean. So, let me talk about what a hypothesis test is. So, when you're talking about a hypothesis test, you are starting with the assumption that the mean is equal to some mu naught. If you're talking about hypothesis testing for a mean, whether it's a T or a Z hypothesis test. Excuse me. And we're typically trying to ask some question about like, what's the question I'm looking for? We're trying to say like, we think maybe the mean is something else. Either it's different than the assumed mean, the null mean or the null hypothesis. And it can either be different where it's not equal, which requires a two-tailed test, or it can be greater than the null mean assumption or less than the null mean assumption, which requires a one-table test. And so we typically choose our alternative hypothesis, HA, based on the context of the problem, right? Sometimes we want to see like, we think the mean is larger than some value. That's going to be a one-tail, greater than. Or we think the mean isn't equal to this value. That's going to be a two-tail because we just care that it's not equal to the value we're talking about. So let's scroll down. So then we talk about how to pick the appropriate test statistic. So if you know the standard deviation, you use the Z statistic and you calculate it as X bar minus the null hypothesis mean divided by the sample standard deviation, which is the sigma divided by the square root of the sample size. If we don't know sigma, then we use the T value instead. And T is going to be X bar minus mu naught over the sample standard deviation divided by the square root of that. I feel like there's something else there. Maybe not though. I feel like it could also depend on the size of n, but I will come back around to that. So then we calculate the p-value. And you can calculate the p-value. It depends on your alternative hypothesis and if you choose a Z or a T statistic. But you're basically looking for, if it's a one-sided test, right, left-tailed or right-tailed, the p-value is the area. If it's left-tailed, it's to the left over here. If it's right-tailed, it's to the right over here. But the p-value is the area that is in that region, either to the left or the right of your test statistic. Again, the test statistic being calculated in this way here, Z or T. And so I will say, sometimes people do this differently. Sometimes people like to say, I'm going to look at the p-value and find the z-score for that. So like for a p-value of 0.05, we can find a z-score of 1.645 and then say, oh, if our test statistic is bigger than that, then we reject. Or we can do it the way where we compare the p-value with the actual area that we find. And so they're both the same, but they're the same but different. So, and then something to remember here, if you're doing a z-test score, you're going to need the exact p-value from the table, right? You're going to look your z-score, you're going to find the p-value on the table. If you have a t-test statistic, you can't actually necessarily find the exact p-value from your table, right? Because the t-scores are only given for certain values like 0.05, 0.025, et cetera, et cetera, et cetera. And we can we'll do some examples in just a minute. And so then if the p-value is less than alpha, we're going to reject the null hypothesis. Or if your test statistic is greater than the z-score for alpha, you're going to reject. So I think that's enough. Let's go ahead and look at this example. And I'm going to talk about both ways of talking about this because I definitely was looking at Nimdari's notes, and he definitely, at least the ones I was looking at, seems to, instead of doing it the way this handout's kind of talking about, where we compare our p-value with the alpha, he likes to compare the test statistic with the corresponding z-score or t-score. So one thing I wish, and I know this is dumb, I mean, it's not that dumb, I wish that my head wasn't always cut off. Like a lot of time I stand here, I'm like, okay, there's my mouth, which just seems like, I'm sure it's not the best on video. Like, really, James, just the bottom half of your face? Okay. But that's what you get sometimes. Sometimes you get just the bottom half of your face. Let me open up the windows a little bit because it feels like it's a little dark in here. Also, I got some new pens. Super exciting. I mean, I know it's not that exciting, but like it's super exciting to me. There's a giant stack of them back there that you guys can see. Also, let me stop sharing my screen so that we can do this right. So here, oh yeah, I was going to open my windows. There's some more light in here. Yeah, that's better. This one's interesting. All right. You guys are right outside my window. They're building a yard outside. Okay. So let's look at this setup. A manufacturer of chocolates claims that the mean weight or average weight of their product, so the claim is that the mean weight, so mu naught, is 368 grams. The standard deviation of the machine that determines the weight is sigma equal to 10 grams. And so now that we know that the standard deviation is actually known, that means we get to use a z-score, regardless of the sample size. If a sample of 49 boxes has a sample mean what do I got here? 364 grams. I guess that might be X bar, not mu. Right, it's a sample mean, not an actual mean. Test the hypothesis. So test the hypothesis. So, and we can, I mean, we should be able to think about what the hypothesis should be. The hypothesis is that we're testing to see if their claim is really true, right? Are their boxes really weighing as much as they say they do? So we're gonna say that the alternative hypothesis should be that the mean is actually less than that number, right? Because it would be fine if it was more than that number, right? We don't care about it being not equal. We specifically care about it being less. So we're gonna test the hypothesis that the mean weight is less than what they claim, 368 grams. So that is our null hypothesis, is that the mean is 368 grams. And the alternative hypothesis is that the mean, do they use is less than 368 grams. Okay, and so there's two equivalent ways of doing this, and I'm going to do them both. So let's find the z-score, the z-statistic of our particular value here. So let's see, I'm going to get, so this is just the normal way of calculating the z-statistic. It's x bar minus the mu naught divided by our standard deviation over the square root of the sample size. And so in this case, it's going to be, let's see, I'm going to get, I'm looking at here, sorry, numbers, 364 minus mu naught was 368 over sigma over square root of n. Sigma was 10, square root of n is square root of 49. So I end up with 4 over 10 sevenths, which is 2.8. I'm sorry, negative. Ooh, negative. Negative 20. Apologies. All right, I get negative 4 over 10 sevenths, which is really negative 4 times 7 tenths, which is negative 28 over 10, which is negative 2.8. And we should, so this one happened to be perfectly like divisible, but you should always round to the nearest 2 decimal places, right? Because we're going to look for the p-value of that z-score. Okay, so here's what we're doing, right? So we're saying, here's our mean, our null hypothesis mean of 268 grams. And over here, here's our actual observed mean X bar of 264 grams with a z-score or z-statistic of negative 2.8. Now, sorry, I forgot one thing at the very beginning, which is important. So before you do all this, you're never supposed to say alpha afterwards. You're also supposed to say, we're going to test with this confidence level. So we're going to use alpha equals 0.05. The problem is if you say it afterwards, you're kind of like, well, I got what I wanted, so I'm just going to test this level. Not holy smokes. Alpha equals 0.05. Okay. So here's what we're going to say, right? So this area here, that's our p-value. If p is less than alpha, then we get to reject H naught, the null hypothesis, in favor of HA, the alternative hypothesis. Now, why is that true? And this is I think this is the important part about understanding what's happening here. The reason we get to do this is because if your I'm not having calculated the p-value yet, although this requires looking at the table. So if the p-value was say 0.03, which I don't actually know what it is yet, that means there is a 3% chance of seeing this value or a smaller value if it were true that this is the mean. So what we're saying with your p-value here is, if this situation is actually true, right? If it is true that the actual mean of the weight of the candy box is 268 grams, then there's only a 3% chance of seeing a value that is 264 grams or smaller. And since 3% or 0.03 is less than the confidence level that we want to reject that, which is 0.05, then we could say, oh, we can say with 95% confidence that we can reject this null hypothesis, or with an alpha level of 0.05, we can reject this null hypothesis in favor of the alternative hypothesis. So that's one way of doing it. And let's actually go. Oh, sorry, did I blow the numbers here? I certainly did. Sorry, yeah. Sorry about that. They're 100 bigger. Apologies. Yeah, good job. Good catch there. So I'm going to look up this z-score in the z-table. So looking at the Namdari z-table here. Sorry, where'd you go? I know I have you linked. 1 second. So that's the other z-table. I guess I should look at the actual Namdari z-table, which is in the book, which is right in front of my face. So looking at the Namdari z-table here, what do I see? So I look up a z-score. So my z-score is negative 2.8, which his z-table does not have. So I look up positive 2.8 instead. So looking at the positive 2.8 z-score, we're going to be given this area here. And when I look that up, 2.80, I get 0.4974. So that area is 0.4974, which means this area is 0.5 minus that. So 0.5 minus 0.4974 is going to be 0.0026. Let me double check the handout just to make sure I'm doing it right. Yeah, that's what it is. So that means this area over here, my p-value is 0.0026. So what that means is there is a 0.26% chance, right? Move the decimal over, right? 0.0026 equals 0.26%. And that's certainly less than my alpha. So what we're saying here is there is there's a little bit more than 0.25% chance of seeing a score this low if the actual mean was 368 grams. So that's a really low chance, right? It's not very likely that we would see a box with this little chocolate in it if the actual mean was 368. This is enough evidence at the alpha equals 0.05 level to say, oh, well, this seems like it's probably not true. I'm going to reject the null hypothesis that the mean weight was 368 grams in favor of the alternative hypothesis that the mean weight is somewhere less than that. And that's all we can say. Sorry, I'm getting a little not hoarse, just like I got a little like, sorry, I know it's, I should probably mute myself next time I do that. So let's see here. Yeah. Okay, so this is the way I typically think about this, but let me talk about the other way to do this, because there is another way which is equivalent, it just is different. So the way Mundari has been doing it typically is he has been calculating this test statistic and then comparing that to the words, to the z-score that goes along with that in the table. So we know, so again, this is a one-tail test. So I'm looking for z alpha, which is in this case z 0.05. So I'm looking for the z-score where the area, so let me draw another picture here. I'm looking for the z-score where the area over there is 0.05. So again, looking at the Mundari table, excuse me. So now I'm looking for the, area here. Use a red pen. So this area here being 0.05 means that there is 0.05, which means that there is 0.45. And we know the score that goes with that. I think it's 1.645. Let me double check. Yeah, it is. It's exactly between 1.64 and 1.65, so it's 1.645. So that z-score is, well, in this case, it's negative 1.645, right? Because we're on the left side. It's a left tail test. So you can either reject the null hypothesis if your p-value, the area to the left of your z-score, or right if it's the other side, right? The area, the small area is less than the alpha level you picked. Another way you can reject your null hypothesis is if your z statistic is further away from the middle than the z-score that's going along with the alpha value. So since our z statistic of negative 2.8 is further away from 0 than the z-score of negative 1.645. Or the way I think he's been writing it is if the absolute value of your z statistic is bigger than the, I think he's just using a positive value there. Yeah, he is. So he didn't even bother doing this. He just said it's bigger than z.05, which is 1.645. It's still the same thing though, right? So if I'm looking here, I'm looking at my table. So here's my z-score, my z statistic of negative 2.8 right here. And over here, here's my z equal to negative 1.645, where the area to the left here, right, that area in orange is 0.05. So either way, we are literally saying the same thing. You can reject if the area in black, the p-value is less than the area in orange, which is the alpha value. Or you can reject if your z-score, z statistic, negative 2.8, is further away from the middle than your z-score for that alpha level, which is negative 1.645. It's the same thing either way, right? You're still saying the same thing. It's just one way you're saying it is this number is further away than this number, or you're saying this area is less than that area. But they both mean the same thing. Okay. So let me ask you guys, before we move on to another example, what kind of questions do you have about that? We're definitely gonna do more examples, but I just want to kind of gauge where you're at with that one. I mean, it's okay if you don't have anything to say. I just want to see. Let me see. Sorry, let me grab this here. Sorry, I closed the thing I had open. I didn't mean to. Okay. Let's do another example. This one is going to be slightly different, but still very similar. So very, very generally, I just want to say, I'm going to say this many times. You get to reject the null hypothesis if it's very unlikely to see the data that you are actually getting. Right? And so the likelihood in this case had to be less than 5%. And it was. The likelihood was 0.0026, which is way less than 0.05. Or you can say you get to reject if the Z statistic you're seeing is really, really far away from the middle, right? So this is way further away than the level that we needed, which was negative 1.645. Okay, so now let me see here. So I can just read it. So let's look at this next one. A tire manufacturer is considering using a new type of material. They need this material to stop the car in an average of 125 feet after the brakes are applied. If there is evidence that it takes more than an average of 125 feet to stop, they won't use the new material. So our null hypothesis is going to be that the average is 125. I'm sorry, it's not H not equal to, H not is that mu is equal to. Right? So, and again, we're saying if there's evidence that it takes more than an average of 125 feet to stop, they won't use the material. So let me ask you guys, what should the alternative hypothesis be? Should it be that the mean is greater than 125, less than 125, or not equal to 125? And you can use, if you want to type in the chat, you can use this for greater and this for less. So what do you guys think? Should it be greater than 125, less than 125, or not equal to 125? If I'm trying to test, if I'm trying to say that I'm going to say if there's evidence that it takes more than an average of 125 feet to stop, I'm not going to use the material. So am I testing to see if it's more than 125 or less than 125? Yeah, I would say more, right? If it's less than 125, we're happy to use the material, right? If it's that it's greater than 125, that's when we're like, oh no, we can't use this, right? We are not stopping it enough. Sure. I should also point out that sometimes instead of writing that the null hypothesis is that the mean is equal to 125, especially for one-tailed tests, sometimes people write that the null hypothesis is that the mean is less than or equal to 125. That might be what, I don't think that's what Namdari is doing. Let me actually look at his notes here real quick. That's not, I don't see him doing that in his examples that I'm reading here. But either way is technically fine. Okay, so let's see here. So they collected data for 9 stops on a test track. So collected data. You might ask, why wouldn't they do more testing? And some possible answers might be it's really expensive to do the testing, like maybe they're burning through tires. I mean, I feel like they would do more testing with this kind of safety, but you know. So here's what they did. They collected data from 9 stops and they got a mean stopping time. So the average stopping time, stopping distance. Yeah, so fun. The person, I'm sorry, this is someone else's example, but the mean stopping time was 128.89 feet. So mean stopping distance is 128.89 feet, which is worrisome, right? It's definitely bigger than 125. So, right, if it was less than 125, we wouldn't even be asking, but well, great, we're going to be fine. With a standard deviation, this is the sample standard deviation of S equal to 3.55 feet. Okay. So should the company use the new material to make the tires? So the question will really, so should we use this new material? So let me ask you guys, if we reject the null hypothesis, does that mean we're going to be using the new material or not? Right? If I reject this and say this, what does that mean? Yeah, it means not, because it means the distance is too big. So if we reject the null hypothesis, it means we're going to say, oh, we shouldn't use the new material. On the other hand, if we fail to reject, or we never say we accept the null hypothesis, we always use the language that we fail to reject the null hypothesis. We're going to say, well, there's not sufficient evidence to say that we shouldn't use this new material, so we're going to use it. Which feels kind of weak, right? It's like saying, well, we didn't find enough evidence to say this, so we're just going to go ahead. It feels like, but that's just the nature of the testing. So in this case, since we don't know the standard deviation and our n is small, right? So here's what I should say. If you don't know the standard deviation, but your n is big, if n is big enough, the t statistic is just the z statistic. So I think if n is bigger than or equal to 30, you just go ahead and use the t statistic. So here's what we've got. We've got an unknown standard deviation, right? We just know the sample standard deviation, and we've got a small n, 9. So we know that our degrees of freedom is 9 minus 1, which is 8. So we're going to do this. Sorry, of course, we're going to use alpha equal to 0.05, which is pretty standard, but obviously we can do different things. Right, so let's calculate the t statistic, or the t score of this data. So the t value is going to be x bar minus the null hypothesis divided, or the null mean, divided by, again, the standard deviation over the square root of n. I suppose this is slightly different because for the other one, we divide by the actual standard deviation divided by the square root of n. Here it's the sample standard deviation divided by the square root of n. So this ends up being, the x bar is 128.89 minus 125 over s, which is 3.55, over the square root of 9. So this ends up being what? 3.89 over 3.55 over 3. The numbers are already written out for me, but just looking at this, right, 3.55 over 3 is not too far from 1. So 3.89 divided by something that's pretty close to 1 should be pretty close to 3.89. It ends up being about 3.29. Okay. Now, here's the thing. For a t-score, we actually can't do it. At least, well, actually, that might not be totally true. You know, you can still do it this way. But so I like the area way. So again, here's what I'm thinking about, right? I'm thinking, okay, here's my t distribution, which is usually kind of more spread out. And here's the middle, right, where mu naught is 125. And then here's my score over here of 128.89 with a t value of 3.29. So the question is, how much area is over here? Well, the problem is the t table doesn't work the same way the z table does, right? You can't actually look at the t table and be like, for a t score of 3.29 with 8 degrees of freedom, we know that the area is some value, right? That is not an option. So instead, what we have to do is we have to look at the values with that degree of freedom and see where our t score lives between. So I'm gonna look at the t table. You guys should too, and I can show you if you want. Well, actually, yeah. Let me just grab them because I feel like this part is moderately important. So let me grab the t tables from his page. Sorry, one moment. Where is it? Okay, I know where it is. Sorry, there's like a million things here. Files, handouts, T table. Okay, I'm share my screen. Share. Okay, so looking at the T table, I'm looking at the degrees of freedom being 8, and I'm basically looking for the T-scores that are bigger and smaller than my T-score in that row. So I look over, my T-score is 3.29, so 1.39, 1.8, 2.3, 2.8. So look, it's between these two values. So my T-score, and let's go ahead and go to the other side here. So my T-score, 3.29. Yeah. So my T-score of 3.29 is between the T-scores of 2.896 and 3.355. And this is the T.005 score. And this is the T.01 score. Yeah. All right, I think I can stop sharing my screen. So here's what this means. So here's my T-score of 3.29. Now, if we were doing it the way Namdari typically does it, I imagine what he would do is he would say, okay, well, I need my T-score to be further away from the mean than the T.05 score, which is neither of these. If I look back at the T.05 score for 8 degrees of freedom on this table, it's 1.86. So here's what I can say doing it the way he's been doing it. I can say, oh, look, my T-score, I literally do it. The opposite value of my T-score is definitely bigger than 1.86, which is the T.05 for 8 degrees of freedom. Since my score is bigger than the T-score at the level I want, we can say that we can reject. Reject is not reject, no, reject. So we can reject the null hypothesis based on this. Or we can do what we just did and say, well, look, our T-score, living right here, and let me do some fun things with colors here. So we know that the T-score to the right of it, 3.355. The area to the right of that is 0.005. And this other T-score that's over here, 2.896, the area that's to the right of that is 0.01. So that we know that the area to the right of our T-score is somewhere between that. And the area to the right of, the area to the right of our T-score, right, this area in black right here, that's our p-value. And so what we can say as well, our p-value is between these two values. So our p-value, now the inequalities are going to go the other direction. So our p-value, whatever it is bigger than 0.005 and is less than 0.01. I mostly care about this part because our p-value is less than 0.01, and I wanted it to be less than 0.05 because that was the rejection level that we set at. So we can say we reject because of this. We can also say we reject H naught because our p value is definitely, we don't know what it is exactly, but we definitely know it's less than 0.01, which is less than 0.05. So here's what we're saying. We're saying that there is sufficient evidence that the average stopping distance is greater than the null hypothesis value of 125 feet. So we're going to reject the null hypothesis that the mean stopping distance is 125 feet in favor of the alternative hypothesis that the mean stopping distance is actually greater than 125 feet, which means we're not going to use the new material because we found the stopping distance, or at least we found sufficient evidence to conclude that the stopping distance is most likely greater than what we consider to be a safe stopping distance. Questions? Let me mention that there are some errors that can happen. So even though, in this case, we rejected the null hypothesis in favor of the alternative, again, we're just making an educated guess based on evidence, but it might actually be true, Maybe we just happen to get a bunch of tires that happen to not be made as well as normal ones, and maybe it actually was true that the average stopping distance was 125 feet or less. That would be an error, that we were saying the null hypothesis isn't actually true, when it is. Sometimes that happens. So let's actually talk about what types of errors, and they do have specific names. So we're going to make this little table. And over here on this side of the table is what's actually true, what's reality. And so you can either have the null hypothesis is true, or that the alternative hypothesis is true. Those are the options. And then we have over here our decision, what we actually concluded based on our testing. So decision, I'm sorry, I need a little bit more table room here. My eraser needs to be replaced. I have plenty of erasers, I just have to replace. So we have the decision from the test. And our decision can either be to not reject H naught, or to reject. Those are the two options. We never say that we accept the null hypothesis. We never say that we reject the alternative. We say we reject the null hypothesis or we do not reject the null hypothesis. So if H naught is true, if the null hypothesis is true and we do not reject, well, then we've done the right thing, We have correctly identified it. So that's correct. And the probability that this happens is 1 minus alpha. We're only going to reject the null hypothesis if we reach a p-value that is less than alpha, and that's only going to happen alpha% of the time, or with alpha probability. So we're only going to inaccurately reject alpha. We're going to accurately not reject 1 minus alpha. And then we have over here where we reject H naught even if H naught is true. And that's kind of the instance where, so we're saying we've got all this data, looks like we should reject, but some of the time that's going to happen where you happen to get data that just happens to be really far away from the actual true mean. And that's going to happen with alpha probability. So this is going to be incorrect, It's incorrect to reject the null hypothesis if the null hypothesis is true. Sometimes it happens, Sampling isn't perfect. And this is going to happen with probability alpha. And this is what's called a type 1 error. When you reject the null hypothesis even though it's true. And typically, that is the error that we are trying to avoid the most. We're trying to make alpha, we usually make alpha pretty small so that we have a low chance of making a type 1 error. We don't want to reject the null hypothesis unless there's really good evidence to do so. On the other hand, it's also possible that my table actually says H naught false instead of HA true. So the null hypothesis isn't true. So then not rejecting the null hypothesis is the incorrect thing to do. and that's a type 2 error. Which we usually write using a Roman numeral. And the probability of that happening is what's called beta, which is some other number. We don't typically calculate beta. And then this other part here where we reject the null hypothesis when the null hypothesis is false, this is obviously correct. And this happens with probability 1 minus beta. And that's called the power, which is a term honestly I'm less familiar with. So similar to confidence intervals, we need to specify the error rates alpha and beta we are comfortable with. The right error rate depends on the context. And so, like I was saying, we typically err on the side of making sure that this is really, really small. Right, in this case, no, this one feels like. So actually, in fact, let me read. So I'm just reading this here. So in this case, a type 1 error, rejecting the null hypothesis when the null hypothesis is true. So in this case, we would be concluding that the tire has a mean stopping time of more than 125 feet when the mean stopping time is 125 feet. That type of error isn't so terribly right. I mean, it depends kind of on what the perspective is. If you're from the saving money perspective versus the people's lives perspective. And sometimes we've seen companies make choices in a direction you would unfortunately imagine would be the other way. So in this case, right, a type 1 error, rejecting the null hypothesis that the mean is 125 in favor of when it's actually true that it is, that's a type 1 error. The type 2 error here would be not rejecting the null hypothesis, right? So not saying that the tire, or concluding that the mean stopping time is 125 feet, even though the null hypothesis is false, meaning that the mean stopping time is actually greater than 125 feet. And that, to me, seems like the more problematic one. Generally, the system is not set up that way, right? We care usually more about type 1 errors than type 2 errors, but be aware that they're both things that teachers like to ask about. So I think that's really, I mean, I could start another example with 2 minutes left, but I probably shouldn't. So I think I will leave it there, but I feel like you guys asked some good questions and we did some good examples. Here again are the attendance and tutoring and the end of quarter evaluations. Please fill out the attendance and fill out the eval and use the tutoring if you need to. And yeah, let me know if you guys have any questions. I will see you all next week. That's all I got. You're very welcome, of course. Good seeing you guys. Oh, office hours. I have office hours this afternoon too. Feel free to drop on by for office hours if you have questions. That's what I want to say. And the link is in the, you know where it is. It's in Canvas. You have a great day too.